For the equation ax equals lambda x, what is lambda called? Eigenvalue. Oops. What is x called? Eigenvector. And what is the set of all x's called? Eigenspace. Okay, so we're defining eigenvector and eigenvalue. There's not much context to this in all of chapter 5. I will preface this by saying eigenvalues and eigenvectors are super important to being able to solve differential equations. So this is like a little bit of a prereq for your ODE class in the spring. But I'm not actually going to show you how they're used in differential equations until next semester. So it's going to feel like this is pointless, but it's not. Okay. Cliffhanger, yeah. Okay, so an eigenvector for matrix A is any vector x such that A times x equals lambda x for some scalar lambda. So lambda is called the eigenvalue of A. So consider the matrix 1, 6, negative 1, 4 is 1, 3 an eigenvector of A. So the definition of eigenvector is does AX equal lambda x for some scalar? So let's see, 1, 3 is my potential x, right? So I'm going to do AX is 1, 6, negative 1, negative 4 times my x, 1, 3. And that comes out to negative 2, negative 6. Okay. So consider negative 2, negative 6. Can I write 1, 3 lambda x? Is there a lambda so that 1, 3 equals negative 2, negative 6? Yes. So negative 2, negative 6 is a scalar multiple of my x. So what is the lambda? Lambda would be negative 2. So is it an eigenvector? Yes. And the corresponding eigenvalue is lambda equals negative 2. A times x gives you a multiple of x. That's what eigenvector means. Okay, slightly different question. Last time I gave you a vector and asked, was it an eigenvector? Now I'm giving you a scalar lambda and asking, is it an eigenvalue? So I need to know, does AX equal lambda x, right? If there's an x that makes this true, then lambda is an eigenvalue. So I'm trying to solve, does AX equal 3x in this case? Lambda is 3. Right, is that true? So in order to solve this, I'm going to do a little bit of manipulating before I actually plug in my values. And this is A minus 3i times x equals 0. I just factored out the x. So this is the equation I need to solve. I just did the manipulation because it puts it into a format that we can use RREF to solve it. So A minus 3i. So A is 3, 2, 0, 1 minus 3 times I. So that's 3 minus 3 is 0. 0 minus 0 is 0. 2 minus 0 is 2, and 1 minus 3 is negative 2. What does this process remind you of, what we're doing right now? Yeah, it's like finding a steady state vector. It's just that when you find a steady state vector, your lambda is always 1. So it's the same process. Finding, checking to see if you have an eigenvalue is just like finding a steady state vector. It's just you're using a different lambda. Okay, so now I want to solve 0, 2, 0, negative 2 times x1, x2 equals 0, 0. So you just augment and row reduce, and you get x1, x2 equals, I'm going to write it out. That row reduces to 1, 0, negative 1, 0, 0, 0. So I've got a free variable. This says x1 minus x2 is 0, which means x1 equals x2. And then my x2 column has no pivot, so x2 is free. But that means there is a solution, right? There are infinite solutions. So the fact that this equation has a solution means that 3 is an eigenvalue. So if we want to find a basis for the eigenspace, that means we want to list every possible x that makes this equation true. The eigenspace is all eigenvectors corresponding to a specific eigenvalue. So this is all x such that ax equals 3x. So basically, that's the solution over there. So we were able to say, yes, lambda equals 3 is an eigenvalue because there was a solution. The actual solution is called the eigenspace. So I would say, well, x1, x2, just writing this in parametric vector form, my free variable is x2. x1 equals x2, and x2 is free, so I have 1, 1 times x2. So you can write it like that. There are lots of ways where you can write the eigenspace. So this is one way of describing the eigenspace. Another way would be to say the span of what? 1, 1. I could write it in, what's that one called? Set builder notation. The set of all vectors that look like AA, such that A is an element of R. I could give a basis. And my basis would just be the vector 1, 1. That's a linearly independent spanning set. So 1, 1 is definitely a spanning set, and a single vector is always linearly independent, so that's my basis. And that's actually how they asked me to write the eigenspace, was to give a basis. Typically, I'll say describe the eigenspace in an appropriate way. You can give any of those answers. All right, that's it.